Alright, in this lecture we're talking about Bernoulli's equation. We're moving on into the next section, and there is numerous derivations for Bernoulli's equations, two of which, or most of which, stem from tracking a particle path and then integrating along a surface and using FMA, where this is along the surface and this is, say, some normal. So if you integrate along the surface, you can derive Bernoulli's equation there. And the other derivation comes from energy methods. I'm not going to derive it here. I'm going to simply write it down and then make an interpretation of it. My interpretation, as well as a lot of people's interpretation, comes from the energy methods. So if you look at the textbook, you can find the derivations. I'm going to leave that to you. You can also find Bernoulli's equation if you go to Wikipedia and just search Bernoulli's principle instead of equation. You'll find a setup there. I'll leave that up to you, but Bernoulli's equations itself can be written in two forms. Pressure, gamma z, rho velocity squared over 2 is equal to a constant along a streamline. Now, you saw a minute ago that I drew something like this. This is the path, say, of a particle in the flow stream, and it ends up somewhere along this path. What this means is that this quantity, say the number is 10 right here, this quantity is still 10, 10, 10, 10. Or if it was 20, it'd be 20 all along it. Essentially, it can be thought of as a conservation of energy with some restraints on it. Now, let's take a look at each of these terms, starting with this term, and make a correlation between the two, between an energy term and this term. Now, when you were in physics, someone introduced you or derived 1/2 mv squared. Now, let me make my v's the same, where this is the mass of, say, a ping pong ball, basketball, whatever, and the kinetic energy was associated with the mass of the particle, basketball, ping pong ball, tennis ball, whatever, the velocity squared, and then half of that. Now let's take a close look at these two, and let's make some correlations between these. The density is nothing more than the mass per unit volume. So I've got a half, and I've got a v squared. Now you have to remember this v and that v are different. One's a volume, one is not. So this term to me looks as though it is the kinetic energy per unit volume. Now let's look at this term. One of the common problems in physics is you have a ball sitting somewhere and you drop it and it moves down in elevation or height, and then your potential energy back up there was something like mgh. And then you'll equate this to that, and you get the standard velocity as a function of height for a ping pong ball or whatever that drops in a vacuum. So how is this term related to that term? Gamma z looks a lot like, well, it's the weight per unit volume times z, which is nothing more than the mass times g over the volume times z. Interesting. So this looks nothing more than the potential energy per unit volume. So now I'm getting a correlation. I'm saying that, hey, wait a minute. These two terms, this is nothing more than the kinetic energy per unit volume. This is nothing more than the potential energy per unit volume. What is that? Well, there's a couple ways to look at that particular term, but one particular way is just to look at, say, a tube and just recognize that pressure is nothing more than force per unit area. Now, if you're looking at mass inside this thing, this is the length, and instead of putting a pi r squared and things like that, that's nothing more than the area. So the volume of this thing is nothing more than the area times the length. So if I were to say this is something per unit, now you realize I ended up going in here and working, getting the volume out of here and the volume out of here. So my goal is to stick whatever this is and stick a volume under it and see what comes out on top. That's the approach that I'm taking right now. So if I'm saying I have a force per unit area, what do I need to put under there to make this thing look like a volume under there? I would say I need to put that. So I put an L on top, L on bottom. So what I've done is copied that down, and this is still nothing more than pressure. But now it's something times force times the length over the volume. Interesting. Per se, think about it like this. Okay, there's a force, there's a total net force pushing this object that way. Now, granted, there's another force over here, but this difference between those, you could look at a delta. The difference between those looks nothing more than force dotted with, say, some distance, you know. And given the fact that this pressure is only along a streamline, like we were saying, this looks nothing more like than the work produced by a pressure per unit volume. So, taking a look at this real quick, this looks nothing more than an energy equation. That's all it is. So it's a conservation of energy in a sense. Now, you've seen something similar to this when you were in thermo. The problem there was that the situation was different. Think about thermo, what you're mostly concerned about is taking a cup of water and then turn it into vapor. So there was a large amount of energy coming into play here. In the fluids, we're not really concerned about phase change, and the temperature that is going to be applied to this is not going to be enough to create a phase change, which means that the predominant energy of anything that would take place would be this energy. Now, when you're changing phase, like in thermo, this portion actually did end up in the first law. The problem was it was assumed out to zero. It was small compared to the energy required to a phase change. In fluids, in this chapter, in Bernoulli's equation, you're not changing phase. So, with that said, now we have Bernoulli's equation. And I'll rewrite it again down here. Let's go further in here and look at common occurrences of this. And I'm just going to write it in C for a constant along a streamline. Let's look at a particular situation. Let's say you had flow coming from left to right here, and it came down into this tube, and let me make a better drawing here, plus I need to put a tap on here. And essentially you had what was a manometer attached to this. let's say the fluid in here had a specific gravity of, say, 1, so it was water, and then you fill this tube with something that had a specific gravity of, say, 5, just for the sake of argument. And you start looking, and you put a ruler up against this, and what you see is this is, say, 0.1 feet. Now, the first thing you know is by looking at this, and from your previous experience, you have something like this. The mass flow rate is the density times the area cross-section times the velocity through that cross-sectional area. And if you have an m dot coming in of some value, you have the same m dot going out. So conservation of mass would tell us that m dot in is m dot out. Now what I'm going to do is I'm going to label 2 spots here. Plus sign here, and I'll label that as 1. Plus sign here, and label that as 2. Now I'm going to contend that a particle that started here pretty much ends up down there and keeps going. And I'm going to work off of that premise. If we start working off that premise, then P1 plus gamma Z1 plus rho V1 squared over 2 is equal to P2 plus gamma Z2 plus rho V2 squared over 2. Now, with that in mind, now I need to contend with what I have. A lot of times I like to make a chart. And my charts are pretty much like this. And then I have a state here. Now I can have 3 and 4 states. In this case I only have 2, but I'm just doing this in case you had more than 2. You could have a third or fourth one down here, but I don't have any of those. But what I do have is this. I know my elevation. Now let's address the elevation first. When we were back dropping marbles or ping pong balls and stuff, we always ended up picking a datum. And then we did mgh, and then we did a 1/2 mv squared. And we equated the two. But the key is we always had to have a datum for this. Now we've already recognized that there is a correlation between that term and my potential energy. And it turns out you have to pick a datum for this. This is again nothing more than an energy equation. So let's pick a datum here, just like we had to do in physics. That means that this value is 0 and that value is 0. Problem solved there. Now, do I know pressure 1? No. Do I know pressure 2? No. But what I do know and can find out from a manometer equation is what P1 minus P2 equals to. And I'll address that in a moment, but after I address this, do I know what V1 and V2 is? No, I don't. But I do know that I can look at a relationship between V1 proportional to V2 through a mass flow relationship. So let's start with a manometer equation. Again, reviewing manometers, I start at this location, go down to an interface, go through that interface, back up to there, and then finally finish it off by going back to that location. That's what I'm about to write. And I'm going to do it in a meticulous fashion, the way we were talking about it several weeks ago. Start at P1. I go down a distance. I don't know what that distance that I go down is, so I'll just call it K for the lack of not knowing what it is. I'll go down a distance K. When I go down, my pressure increases. Now, this is my specific gravity, and this is gamma of water, but what I'm going to do is just call this gamma, say, we'll call this gamma A, and we'll call this gamma B down here. So gamma A. Now I'm going to go down even further, plus 0.1 times gamma A is equal to, and I need to label this. So I'm going to label this location D, and this one location E. So that's going to be pressure at D. Now I can start at pressure at D. I can move up 0.1 times gamma of B, which we'll address what that is in a little bit, and I'll end up at pressure E. Then my final step is to go up from E back to 2 minus K. I'm going through gamma A is equal to P2. Now, just like we did before, I can go in here and I can erase and move this to the other side, and I can move this to the other side. It becomes minus equals 0, and then I add them all. P1 plus K gamma A plus 0.1 gamma A minus PD plus PD minus 0.1 gamma B minus PE plus PE minus K gamma A is equal to P2. Now, of course, what you get is you get these two canceling each other and these two canceling each other. But you also get this term and this term canceling each other, which gives you back P2 minus P1 is equal to 0.1 gamma A minus 0.1 gamma B. Now you can address the gammas, and you could say, well, it's 0.1 times gamma A minus gamma B, but gamma A is associated with that, and gamma B is associated with this. So I can basically take it and go one more, 0.1 gamma of water times SGA minus SGB. Now, this was basically SGA, and this was SGB. So that being the case, point 62.4 pounds per cubic foot, but this is already in a foot. So what we're looking at is SGA 1 minus 5. And what we end up with here is minus 24.96 pounds per foot squared. So we've addressed the difference between these two. In fact, let's start trying to deal with this a little bit by recopying this equation down after we do one more thing. We haven't dealt with the difference between these two yet. First of all, I didn't include what the areas were, so let's go ahead and kind of specify. I'll say area 1. I could put a diameter, but that would just complicate issues for the moment. So I'll say my area 1 is equal to 1, and I'll say my area 2 is equal to, say, 0.2. Now, with those two, I can basically address this by looking at rho A V1 is equal to rho A V. Now the density is not going to change, so it depends on which one I want to basically focus on. Do I want to find or eliminate the velocity 1 or the velocity 2? Now the fact of the matter is, it really doesn't matter per se, so I'll just represent it like this. Wait, let me fix that. A2 over A1 gives me so I have a couple of facts here, and I'm going to copy these facts down. I have this fact, and I have this fact. P2 minus P1 equals to minus 24.96 pounds per square foot. There's fact number 1. My other one is V1 is equal to 0.2 V2. And then this came from the manometer equation, and this came from conservation of mass, and my Bernoulli's equation, which I'll rewrite again. Now, first, since Z1 was equal to Z2, these simply cancel out. Now, since I have this written as P2 minus P1, I'm going to take this term and put over here, take this term and put over here. Now, right off, you see something interesting here. I see that I can actually get one piece of information from here and the other piece of information from there. So let me go on and do this. What you would end up with is minus 24.96. Over here, you're looking at what right here? What is the density? Okay, now let's review something here. From 1 to 2, we're going through this fluid that has a specific gravity of 1. I can weld these off or cut them off, and the gamma B down here doesn't matter at all. So this flow, this gamma, is actually gamma A, density of A, gamma of A, and density of A, because all the fluid in here is that, and that's gamma A, and that's the where the flow was occurring. So with that being the case, I can go back and recognize that since gamma or Sg of A was 1, that's nothing more than water. So that becomes 1.94 slugs per cubic foot, and then I'm looking at V1 minus V2. Now again, I can from here I can borrow that equation. Now if I do that, I'm looking at V1 and I insert that, so I get 0.2, and then that's squared times V2 squared minus V2 squared. And so now I need to pull out my calculator after one more simplification, that is 1.94 over 2. I can pull the v2 squared out. 0.2 squared minus 1. Now I'll pull out the calculator, and I get minus 0.9312 is equal to minus 24.96. Now, I'm going to leave a space because I'm going to come back and address units in a second, but I'm going to say V2 is nothing more than the square root of 24.96 divided by 0.9312. And we really do need to address the units here because this is something that may appear to be difficult but actually is not. So I get a velocity of about 5.177, say, feet per second. Let's address the units, say, back up here. Now if you look at this, this could be very annoying. What you have here is slugs per cubic foot. What you have in here is a velocity squared, so you have feet squared over second squared. Over here you get pounds per foot squared. So at first glance, you may look at this and get very annoyed by this until you realize F is equal to MA, a pound's equal to a slug, a foot per second squared. However, maybe we want to move the slug. So what you've got over here is you've got a force unit here and a mass unit here. You got to give up one of these for the other. Which one you do is kind of up to you because they all come out in the wash. But let's just give up, say, a slug here. So a slug is nothing more, leave the pound over there, take a second squared across, bring a foot underneath, and then stick it in right there. So if you do this, you get a pound, a second squared over a foot, but then that's over a foot to the third, so that's a foot to the fourth, and then you get a foot squared over a second squared. Those disappear, two of those disappear, and lo and behold, you get the same units. So although these looked like they were not the same units, they actually are. Now, from this point forward, you can drag the pounds per second squared if you want it. I mean, a pound per foot squared if you want it to. But it doesn't matter because your units canceled out at this particular point, and they are correct. So, we've seen this is one of the most classical problems here, in that if you were given a situation like this, attached a manometer to it, had a reduction in the area across here, you would find that you can actually determine the flow rate through this device. Now, let's make some judgments here. First, let's go back and look at this and ask some simple questions. So I'm going to put a green box around all these questions, and then these are thought questions. Okay, is P1 greater than P2? Well, first of all, you can look down here and find out. P2 minus P1 is a negative number. So you could sit there and say, in our particular case, let's look at this and say, let's move the 24 over, it becomes positive, and let's move the other one over. P1 is equal to P2 plus 24, and let's go ahead and say roughly 25. It's approximately equal to that, plus 25 pounds per foot squared. So P1 is larger than P2. Or you could say P2 is less than P1. Consequently, since the pressure at 2 is reduced, it pulls the fluid up towards it, which is why this interface over here at E, this interface right here at E, is higher than the interface there at D. So that being the case, you've made an assumption there, or you've not made an assumption, you made a discovery. You go in here and you say, ask another question. Let's put the other question. Is V1 greater than V2 or vice versa? And of course this you should already know. The velocity 2 is actually faster than the velocity 1 because it's constrained down and has less area to go through. So it's picking up speed to go through there. Now, let's take a close look at these things that we've discovered and move them down and relate them to Bernoulli's equation. So I've copied these down here by themselves. Let's put a line through here and let's take a look at something. Velocity 2 is greater than velocity 1. So if I were to say this was higher than this, then P2 is less than P1. And these are equal, so they don't play a role. Now we have to realize that the whole thing here is these equaled. So if you drop the pressure somewhere, you have to increase the velocity there in order to offset and equal the left end of the equation. So anytime, so here's our typical case. You knew that the velocity here was much greater than this. Since the velocity is greater, pressure has to drop. So this pressure is lower than this pressure. Now, there are many different arguments on this, but if you take a wing, for example, take a, say, a NACA 4412. I'm not a good drawer, but essentially it has a flat profile on the bottom, almost flat. And if you look at the actual equation for it, you'll see that it's flat for a while until it starts curving up. Now, there is a fault in this logic, but in effect, let's say that this airfoil is moving in this particular direction. So it's moving along, and eventually, let's say it splits these particles and one moves underneath and the other one moves across the top. Now, kind of a rudimentary argument is that since this particle on average went a larger length than the bottom, that generally speaking along the top, the average velocity of the top just ever so slightly greater than the velocity on the bottom, because they had to go a little bit further distance. Well, if that's the case, if the velocity of the top is that way, let me realign these. Pressure on the top slightly less than pressure on the bottom. So that means the pressure on the bottom is greater, pushing this thing up a little bit. And if the exposed area is large enough, you can get some lift out of this. And consequently, if you put a NACA 4412 in a wind tunnel and you make this bottom flat with the flow, you'll get some lift out of the thing. So Bernoulli's equation can be explained that way. Another thing you've seen before, it's fertilized spreaders. You go to Lowe's and you can buy a fertilized spreader, or Home Depot, or any of your hardware stores, Ace Hardware, Sears. You can go to Walmart, any Target, any of them, and you can find this. It's basically a device. It's round, has a kind of a barrel on it. You fill this with some kind of liquid, and you put a top on there, and the straw goes down in there. Essentially, a straw goes down into there, and you attach it to a garden hose. And I'm not a great drawer, but I'll do the best I can. What happens is you start spraying, and you can find this. You can put soap in there and wash your car with it. You can do all sorts of things. Here's what happens. There's a hole in here, so this is exposed to the outside top air. So this is nothing more than atmospheric pressure on the top of this fluid. However, the garden hose is coming through here. It picks up speed here, thereby dropping pressure. The pressure drops enough that it starts pulling the fluid up the tube, mixing it, and spraying it out on your car or your garden or whatever. If they make this diameter or area small enough, then it can drain every bit of fluid out of this by just simply sucking it up that tube. This is another effect of Bernoulli's. Another effect could be, let's say you take a cylinder. You drill a hole through your cylinder. It doesn't have to necessarily be a cylinder, but it is nice to have it a cylinder because of the mathematics. And then you attach an air supply to this. So all of a sudden you're shoving air in here. You can shove water as well. Then if you look at this, but it's not as nice there. If you look at the side view of this, this is what you have. You have something with a hole through it in which you're pushing air through there. Attach it to something or put it on something like that, and then what happens is the air turns and goes through in this particular direction. Now your first inclination is say this was a very light object, that say you would plug this in, your first reaction may be it would blow it off. But in fact, it does the reverse. As long as this diameter is much, much smaller, if D1 is really, really small compared to DO, outside diameter, it will pull this thing closer to it. Now why? If you look at this from a top view, so you're a person looking down at this, and what you see is something, let me try this again. You see a big circle, and you see a hole with the air coming at you or leaving you, it doesn't matter. Out here, you have particular air supply going out. Now, if you look at this gap, and you say to yourself, what is the area of the exit here? The area of the exit is nothing more than 2 pi, say R outside, times the gap. Now if you take any particular location where this is R, where maybe I'll make it a small r, the area as a function of r is nothing more than 2 pi r times the gap, given that the gap doesn't change all along here, which it shouldn't unless you design it differently. Now this means that AR VR is equal to A exit V exit. This means that the area, since this R is less than R out, then you have your area as a function of R smaller. Therefore, VR is much larger here. Again, PR plus gamma ZR plus rho VR squared over 2 is equal to P at the exit plus gamma Z at the exit plus rho V at the exit squared over 2. If in gauge pressure, this is 0. These two equal each other. So your pressure of R is equal to rho VE squared over 2. Well, I could take VE squared minus VR squared. What did we just find out? VR squared, or VR, is always greater than VE, which means that the pressure at some location R in there is equal to a negative number, meaning it's pulling a vacuum. So whatever this object is, the pressure is a vacuum in here, and pulling, unless there's holes drilled in this thing, it's pulling it up very tight to this. Okay, so recapping where we started was we started with the concept that Bernoulli's equation was actually an energy equation. We took one case. This is the standard case that generally people take, in which a manometer is attached to two sections of different diameters, and fluid is run through here. I basically am a big supporter of using this chart because it tells you right off what you need to work in between. Then if you're just very meticulous, you make sure you use your manometer equation and your mass flow equation. You only use a manometer equation if you see a manometer sitting on there. Then from those two, you can work out, in our case, we found out the flow rate. And then we took off and looked at some other common instances where Bernoulli's equation has an effect in your basically day-to-day lives. So in the next lecture, I'm going to go in and work a series of problems using Bernoulli's equation, and these will be problems that you're very responsible for the test in the next section.